Assalamu alaikum, everyone, and welcome to the Artificial Intelligence and Radiology Center Internship Program. Before we dive into the technical mechanics of artificial intelligence, consider a standard case in the emergency department of a Pakistani government hospital. A patient arrives with shortness of breath, a high fever, and a rapidly dropping oxygen saturation level. Within minutes, the attending physician orders a chest X-ray. Now, consider what follows. Executing this request initiates a complex chain of decisions, operational dependencies, and potential delays. Every link in this chain directly dictates whether that patient survives. This diagram illustrates a common misconception that radiology is a two-step transaction, where you capture an image and hand back a report. In practice, this equation does not exist. Radiology is a systemic clinical service operating across 7 distinct sequential stages. Maintaining this sequence requires the coordination of referring clinicians, technologists, radiologists, and digital infrastructure under heavy patient loads. This leads to the foundational rule of this course. AI does not work in isolation. It must be mapped to these specific clinical systems. Because the workflow functions as a unified pathway, a failure at any single node cascades downstream, compromising the final diagnosis. We will audit this system by mapping a patient's journey through these stages. We begin at Phase 1, the clinical decision to image. Ideally, a clinician evaluates symptoms to decide if imaging is clinically necessary. In many local contexts, severe time constraints force physicians to use imaging as a diagnostic shortcut. This results in an immediate artificial spike in radiology volume. That volume flows into Phase 2, request handling, where the imaging order reaches the department for processing. The bottleneck here is the absence of a structured triage system. Without severity protocols, life-threatening emergency cases are dumped into the same queue as routine outpatients. Next is Phase 3, image acquisition. This stage relies on the technologist to manage exposure settings and physical positioning to ensure diagnostic clarity. High patient volumes often strip technologists of the time needed to properly position uncooperative or critically ill patients. When skips triage meets rushed acquisition, the result is suboptimal scans and repeats. The system is overwhelmed before a doctor even sees the image. In a digital baseline, Phase 4 images transmit instantly to a picture archiving and communication system, or PACS. However, many centers still rely on physical CDs, printed films, or manual uploads. These methods create immediate reporting delays. These images eventually reach Phase 5, the reporting queue, where they wait for a radiologist's interpretation. High-volume centers typically use a strict first-come, first-served approach. There is no automated mechanism to flag case severity. Consequently, a time-sensitive emergency case can be buried at the bottom of the work list beneath dozens of routine scans. Without intelligent prioritization, the workflow prevents radiologists from treating the sickest patients first. Logistics become a matter of survival. In Phase 6, interpretation, the radiologist must perform high-level mental pattern recognition while integrating the patient's clinical history. At this stage, cognitive fatigue sets in. Continuous screen exposure and long shifts tackling massive backlogs deplete the radiologist's focus. This exhaustion leads directly to missed findings and the delayed recognition of subtle pathologies. Once identified, the findings move to Phase 7, reporting and communication, where the result is sent back to the referring clinician. Breakdowns still occur here. Communication gaps mean that even when a radiologist identifies an urgent finding, it is not always escalated to the emergency department quickly enough. A broken communication loop renders the entire diagnostic journey useless, regardless of how accurately the scan was interpreted. Analyzing the system as a whole reveals 5 core systemic weaknesses across the clinical pathway. First, the total lack of triage mechanisms. Second, the massive workload imbalance between patient volume and available radiologists. Third, variable image quality caused by rushed acquisition. Fourth, delayed data flow due to outdated infrastructure. And finally, the hard limits of human cognitive endurance under time pressure. The Pakistani radiology workflow is an incredibly high-volume, resource-limited clinical environment where every single second counts and time is the most critical constraint. We approach artificial intelligence as a targeted workflow intervention tool rather than a standalone scanning technology. At Phase 5, the reporting queue, Algorithmic triage instantly flags urgent cases. This lets critical patients bypass the first-come, first-served bottleneck. At Phase 6, AI acts as a safety net during long shifts, supporting interpretation and reducing the impact of cognitive fatigue. This entire internship program focuses on discovering exactly where these AI tools can make a measurable, life-saving difference in real, everyday clinical systems. We are mapping the specific physical and digital points where patient care degrades in the modern hospital. This is our starting principle: clinical reality first. In radiographic AI development, there is a pervasive assumption that algorithms will operate on pristine, perfectly formatted data inside frictionless networks. We call this the ideal data fallacy. Designing for an optimal environment is a theoretical exercise. When these models meet the physical constraints of a functioning hospital, the mismatch between theory and reality becomes clear. To understand these constraints, we are focusing on the high-volume, resource-limited environment of the Pakistani healthcare system. Accounting for these hardware limitations and throughput pressures is the prerequisite for building an effective radiographic AI. To find the gaps in care, we must trace the chronological journey of a single radiographic image from the console to the doctor's screen. Every image begins at Phase 1 with the initial order. However, our analysis targets the transition to Phase 2, image acquisition. We are looking strictly at the space between the imaging console and the final reporting screen. The delays found in this section of the map are structural features of the current system, rather than isolated errors. To fix the system, we must first isolate the exact bottlenecks occurring chronologically down the chain. Phase 2, image acquisition, is the most underrated step in the radiographic chain. This phase is defined by the role of the technologist, who sits at the center of the data flow. In Pakistani hospitals, these technologists manage an extreme volume of patients. Under this throughput pressure, a technologist may be forced to scan an entirely new patient every few minutes. This time deficit leads to physical compromises. Positioning can be slightly off, and machine settings may be suboptimal for the specific patient. The situation is further complicated if the patient is in pain or uncooperative, leading to motion artifacts in the image. These acquisition pressures degrade the raw data before it ever reaches a digital network. In some health systems, a poor quality image is simply repeated until a clear scan is achieved. In resource-constrained environments, the luxury of a repeat scan is rarely available. This creates a permanent clinical baseline known as diagnostic uncertainty. Radiologists are forced to formulate critical diagnoses based on these suboptimal one-shot images. On the left, we see an ideal chest X-ray. On the right, the reality. The image is rotated and the lower edge is clipped, meaning critical anatomical information is missing. AI developed for this environment must treat this uncertainty as a standard variable rather than an outlier. An algorithm trained exclusively on perfect images will fail when confronted with the reality of diagnostic uncertainty. The workflow now advances to Phase 3, image availability. In an ideal state, the image is transmitted to a PACS, a picture archiving and communication system, instantly. In many local centers, this instant transmission is replaced by significant physical friction. This friction manifests as an ongoing reliance on burned CDs and printed films. Even digital systems face delays, with local network uploads from the console often stalled by limited bandwidth. These infrastructure gaps turn a data transfer problem into a severe chronological delay. Every minute an image sits on a technologist's console is a minute lost for the patient. We reach the final destination, the reporting queue. This queue represents the most critical vulnerability in the entire radiographic system. Imagine a digital stack of 200 studies. In a first-come, first-served system, the images are processed in the exact order they arrive. If the radiologist starts at the top, they may spend 20 minutes clearing routine cases. Now consider a patient with a collapsed lung entering this same queue. Because of the sequential processing model, this life-threatening case is buried at the bottom of the list. The radiologist is occupied with routine work while an acute pathology waits unseen. The delay is a result of the queue's sorting logic. The system fails to prioritize the most urgent data before it reaches the specialist. Let's review the journey from acquisition to the reporting screen. Acquisition pressure creates the baseline of diagnostic uncertainty. Infrastructure lag delays the physical and digital transfer of data, and the sequential reporting queue buries urgent cases under routine ones. Designing medical interventions requires us to account for this specific clinical reality. Our task is to engineer intelligent systems that can identify these gaps and disrupt the standard flow of data. Using technology to prioritize acute pathologies over routine queues is the primary mechanism for reducing time to treatment. Many engineers arrive in medical AI believing healthcare data is cleanly packaged, prepared, and ready for an algorithm. They assume clinical radiology operates as an isolated mathematical function. The standard mental model dictates a linear process. A patient arrives, an image is taken, the AI processes that image, and a diagnosis is output. This pipeline exists only in theory. It cannot survive contact with an actual medical environment. In practice, radiology is a volatile, multi-agent clinical pipeline. That pipeline relies on the interconnected actions of clinicians, technologists, and radiologists. It also runs on digital infrastructure that often strains under high patient loads. Before you write a single line of code, you have to map and understand this chaotic architecture. Consider a government hospital emergency department in a city like Lahore or Karachi. We must uncover the hidden chain of decisions made before a medical image is ever generated. These upstream decisions dictate the performance and the failure rates of the models you build downstream. You cannot deploy an effective model until you first understand the noise in the clinical system where it lives. This network diagram represents an emergency department. The workflow begins at the outer edges. The pipeline starts biologically, driven by patient symptoms like fever, cough, and dropping oxygen. Hundreds of these patient profiles enter the network simultaneously, converging on a single processing node, the clinician. A single doctor might be tasked with evaluating hundreds of complex cases in one shift. One of those cases is a patient with severe respiratory distress, whose oxygen levels are actively dropping. The relentless volume of critical inputs pushes the clinician past their processing limit. This biological overload is the catalyst altering all downstream data generation. At the point of failure, the overwhelmed clinician still has to triage that critical respiratory patient. They need an immediate definitive answer, but lack time for a thorough manual assessment. The clinician adapts by taking a diagnostic shortcut. On the network model, this shortcut appears as a bypass. The clinician generates a chest X-ray request to sidestep manual evaluation. This localized decision instantly alters the digital ecosystem, sending a spike of data requests down the bypass pathway. In government hospitals, this shortcut is the dominant systemic pattern. This pattern multiplies the raw volume of data flooding into the radiology department. It compromises the baseline validity of the imaging queue because requests are driven by time constraints rather than strict necessity. Developers must realize not every image in a dataset is essential. Clinical overload floods the radiology infrastructure with rapid, unfiltered data requests. Tracking this downstream, requests arrive at the radiology department, accumulating in a vertical stack, the queue. This is the first major system bottleneck. A flashing red packet for the critical patient arrives simultaneously with a gray packet for a routine checkup. The bottleneck occurs because the hospital system lacks digital triage capabilities. In a purely chronological system, life-threatening cases are forced to wait behind routine, non-urgent ones. Without digital triage, those packets enter a flat, untagged array. The critical red packet is buried at index 45, beneath dozens of routine cases. The critical biological signal is now mathematically obscured within this rigid structure. For the system to process data safely, it requires metadata tagging for clinical urgency. From the perspective of an AI developer, this unprioritized stack looks like random, unstructured data. In informatics, we define this phenomenon as clinical system noise. This noise occurs entirely upstream, before a single image pixel is ever analyzed. Ignoring this upstream noise ensures that an AI intervention will fail the patient, even if the mathematical model is highly accurate. This diagram shows the entirety of the flawed hospital network. Notice the unregulated gap between the clinician and the radiology department. This gap is the optimal point of intervention for clinical data scientists. We can introduce a systemic fix, an algorithmic block that intelligently sorts the diagnostic shortcut before it reaches the queue. The queue autonomously sorts itself, instantly elevating the critical red packet from index 45 to index 0. Algorithmic pixel reading power is irrelevant if the critical patient is left to wait at the bottom of an unsorted digital stack. As you enter the field of medical artificial intelligence, you must redefine your scope. The true frontier of the discipline lies in optimizing the end-to-end workflow. This requires a professional shift toward engineering resilient clinical data architecture. Building tools for the real world requires treating the entire hospital pipeline, from the overcrowded ER to the digital stack, as your ultimate algorithmic architecture. Thank you.